So, welcome to the continuation of the lecture on the time harmonic form of Maxwell's equations. Let us go to the lecture. Now, let us start with the generalized current we discussed in the instantaneous domain and write down the generalized form of the current in the time harmonic domain. So, we have already written that previously, we will write that down again. J t is E plus J I. So, J t is sigma plus j omega E plus J I. So, we had y cap E plus j that is equal to y cap omega E plus j I, where y cap omega is sigma plus j omega epsilon. Next, we have m t, we have already written that, we are familiar with this. M t is j omega mu h plus m I, that is equal to z cap omega h plus m I, where z cap omega is j omega mu. So, if we now perform this operation E dot j t star, as we are required to do, we have to perform E dot j t star, we saw that previously. So, we perform this operation E dot j t star, we will get E dot sigma minus j omega epsilon E star plus j I star. Note this minus sign. Okay. This comes as the result of the conjugation operation here. So, then performing E dot E star, it will become mod E square sigma minus j omega epsilon plus E dot j I star. And that is equal to sigma mod E square minus j omega epsilon mod E square plus E dot j I star. Similarly, H star dot empty, H star dot empty will be H star dot j omega mu h plus m I and that is mod h square j omega mu plus h star dot m I. Now, the average dissipated power, the average electric and magnetic energy densities are P d tilde as sigma mod E square W E tilde as half square and W m tilde is half mu h square. So, equation 40 can be written as finally divergence of S mod E square sigma minus j omega epsilon plus E dot j I star plus mod h star square j omega mu h star dot m I equal to 0. This 41. So, this is just by direct substitution, and this term P s hat is minus E dot j I star plus h star dot m I it is a complex power density supplied by the sources. It is a complex power density supplied by the sources and P f cap is divergence of S. Therefore, we can write P f cap plus P d tilde plus 2 j omega this is W E W m minus W E W m tilde minus W E tilde is equal to P s cap. So, this is the power flow term, this is the power dissipated term, this is the stored energy term, this is the power supply term. So, this is for a point relationship. Okay, this again shows that the power supply term is broken up into the power flow, the power dissipated and the stored energy terms. So, now similarly for a region we have P d is equal to mod E square d tau. We just integrate over the region of space similar to the instantaneous domain. W A tilde is half epsilon mod E square d tau. W m tilde is half mu d tau, that is W m tilde d tau, and big P s cap is similar to the instantaneous domain. This is over a region, the power supplied by the sources in the region E dot J I star plus H star dot M I d tau. So, therefore, integrating both sides of 42, so let us write this as 42 integrating both sides of 42, we get P f cap plus P d tilde plus 2 j omega W m tilde minus W e tilde equal to P s cap. This is equation 43. So, what is essentially happening when we discuss the time harmonic form, it is very apparent of the power conservation theorem in a point and in a region. So, if I consider for instance a dipole antenna. So, you see it is being fed by, let us say, a coaxial cable, and it is radiating. So, the power supplied by the sources, it is saying it is being broken up into this term and this term. Note that this is a purely real term. This term is purely real. As you can well see, this term is purely imaginary. and the power supplied by the sources will consist of real and imaginary parts. Okay. And this will consist of again real plus imaginary parts. So, as I increase, let us imagine a spherical surface. It is an imaginary spherical surface. So, it is S1. So, as I surround this dipole with a spherical surface, I try to find out, I try to understand what is happening to the power which is crossing this spherical surface. So, inside this surface, in this region, inside this region, we have the stored power. This stored power is given by what? This stored power is given by the volume integral, because Wm and We are nothing but the volume integrals. So, we are integrating over a volume of space. If I increase the radius of this sphere, if I increase this radius of the sphere to, let us say, S2, the volume enclosed will be more, and therefore, the stored power will be more. So, this is called the near field of the antenna. So, as you increase, keep on increasing the volume, the stored power, the circle, the spherical shell, the imaginary spherical shell is accompanying, it is encompassing a larger radius, and therefore, these terms will continue to increase, because similarly you are enlarging the volume. So, this is contributing to the purely imaginary stored energy term. However, you see that this the power dissipation is happening in this surface, the conductor surface, ohmic loss in these surfaces. This is where the power dissipation is taking place. So, this is fixed in this region of space. It does not vary with the increase of spherical radius. So, it is happening inside. Also, this term is due to the sources inside this region. So, that is also fixed. So, what is happening to the other part, which is the real and imaginary parts? As you cross different surfaces, the real part, which is the power radiated, will be the same. The real part of PF cap will be same as you cross different surfaces, because that is the power radiated. The imaginary part of this term plus this term is going to contribute to the imaginary part of the power supplied. As you go to increased radius, this power flow becomes purely real. The imaginary part slowly diminishes. So, this imaginary part is completely taken by this. If you were to increase the sphere to a limiting value, this value will saturate. It will come to a particular limiting value, and beyond that it is going to stay virtually constant. You are in the far field region where this power PF cap is totally real. Further increasing this will not increase this, and this will stay as real. So, this term you see in the near field, this term and the imaginary part of this term in the near field, it is contributing to the imaginary part of this. Why is this important? This is important because we want to match this to the 50 ohm load. On the other side, on the other side of this I have a 50 ohm coaxial line. So, this input impedance has to match to the 50 ohm feed. Okay. So, it must therefore be remembered that the reactive part of the power supplied is the same as the stored energy part plus the imaginary part of the power flow, that is contributing to the reactance of the system, and this has to be cancelled in order for this system to be matched, for this dipole to be matched. Okay. So, we told you that this matching problem is something like this. And let us say, so this is the, let us rub this part, this is the resonant frequency, this is the X in and this is the R in, with Z in equal to R in plus J X in. This is the resonance of the system. Typically, the resonance of any antenna, let us say if it is a let us suppose a spherical, like a multilayer sphere, resonance of this. So, this is epsilon 1 mu 1 epsilon 2 mu 2. A typical example to this might be a system like this, where I have a like a multilayer resonator antenna, epsilon 1 mu 1, that is epsilon 2 mu 2, and this is epsilon naught mu naught, fed by a coaxial probe. So, normally this resonance frequency is the loaded resonant frequency, that is with the excitation of the probe, the source included. So, we have included the source in the problem. So, it is the inclusion of the source. So, the point where the reactance curve crosses the 0 axis is where the resonance occurs, there the input resistance peaks. This is leading to the radiated power. So, we can say that we want to maximize the input resistance, for any kind of antenna in order for the antenna to radiate. But we must also remember that this same input resistance is responsible for the matching, because R in has to match, I said it has to match, contribute to the matching with the source. So, it is best that R in should be equal to 50 ohm at its peak. But I told you that the complex power is mod I square times Z, and that is equal to mod I square times R plus J x. And that is equal to power real plus J power imaginary. We now, our previous analysis shows that this power real, which is the radiated power, which is the real part of this term, Okay, it depends on the system, it depends, it is directly dependent on the amount of real power which will be emitted or radiated by the dipole. So, we have no direct control over this or to ensure that this will correspond to a 50 ohm radiation resistance. We can try to adjust the location of the feed to get a match. We can adjust the location of the feed to get a match such that this peak corresponds to 50 ohm. If we can get a match with by varying this feed location, we can match this point to the 50 ohm line, if this is 50 ohm. If instead of 50 ohm, if this is 70 ohm, because on that number we have pretty much less control, little control. So, if that is 70 ohm, then we have to use a quarter wave transmission line in order to match this to a 50 ohm load, but we have to make sure that we are operating at the resonance frequency of the antenna. So, that the reactive load is 0. So, this is called the loaded resonance. It is called the loaded resonance. The concept of loaded resonance is used to match a antenna or any kind of guided structure with its feed. It is distinct from what we call source free resonance. This can be well illustrated by this kind of antenna structure. For example, if I were to compute the source free resonance of this, I would say, because it is source free, it is independent of the source, there is no source which is exciting this structure. Okay. We would just match the electric and the magnetic fields here, and we will match the electric and magnetic fields there. In fact, we can work with even a single layer. We can take a single layer, we can take a single layer of antenna epsilon r epsilon naught, and we have a single layer. By image theory we replace the ground plane. So, this is my ground plane which is infinite in theoretically infinite in extent. By image theory we replace the ground plane, okay. Then have the probe, and this is epsilon 0. Now, when we are dealing about the source free resonance, we consider only this sphere. So, this is epsilon r, this is epsilon naught. So, we will come to that, but what we do is that we expand the fields inside this sphere. So, let us say this is the z axis. So, this is the theta direction and this is the phi direction. So, the potential functions inside this sphere will be described by this kind of functions p n m cos theta along the theta direction, okay, e to the power j m phi along the phi direction, and along the radial direction will be j n cap k 1 r. That will be its variation here, and we will sum up over this m and n. Okay. So, it is going to be a summation over m and n something, and then we are going to say So, we are going to sum up over m and n, okay, and we are going to match the fields here, that is the E theta 1 will be equal to E theta 2, where E theta 1 will be the tangential fields here, will be equal to E theta 2. E phi 1 will be equal to E phi 2. Then we will have H theta 1 equal to H theta 2, and we will have H phi 1 equal to H phi 2. So, we will match these 4 sets of fields, and once we match them, we will come to an equation called a characteristic equation. We will explicitly go through this procedure when we do the resonator. Therefore, I am not explicitly writing the explicit equations for this here. But we will come to the characteristic equations by matching the fields. In this case, in this solution we assume that the source is absent, that the fields have been established by the source, but the source itself is absent. So, the roots of this characteristic equation will yield the infinite modes of this spherical ball. So, we will label the roots in terms of n, m and p. In fact, those roots will be independent of m, but will depend on n only. Okay. And p, for a given value of n, the roots will be marked as p equal to 1, p equal to 2, p equal to 3, like that. So, n equal to 1, p equal to 1, p equal to 2, and so on. N equal to 2, it will be again p equal to 1, p equal to 2, and so on. Okay. But it must be remembered that though the resonant frequency is independent of m, the fields will depend on m. What does this? Why we do this exercise? Why it is important to us? It is important to us because through the source free modes, let us say we have obtained a match with this system. For this system with the coaxial probe, with this probe we have obtained a match at this frequency minus 20 dB, and that is 0 dB, and this is reflection coefficient mod S11. We have obtained a match at this frequency. So, we want to know which is the mode which is responsible for this resonance. As I told you, this mode is found by, this resonance is found by matching the electric fields and the magnetic fields. And by the way, the inside radial function is going to be, this is called the Shelkunov type Bessel function, and outside in this region the function will be the Shelkunov type Henkel function. So, if this is epsilon 1 mu 1 and this is epsilon naught mu naught, so k 1 is going to be omega root epsilon 1 mu 1 and k 0 will be equal to omega root epsilon naught mu naught. So, this is k 0 and that is k 1, because this is located in this region, this is located in this region. The reason why we choose different functions is that the Shelkunov type Bessel function is the only function which is finite at r equal to 0. If the point of computation includes the point r equal to 0, the Shelkunov type Bessel function is the only function which is finite. Similarly, the Shelkunov type outgoing Henkel function, it is Hn2 denoting the outgoing Henkel function. Okay. It is exponentially decaying and therefore, satisfies the radiation condition at r is equal to infinity. So, therefore, when we match these two fields, two sets of fields, the electric fields and the magnetic fields, using these potential functions, from those potential functions we find out the fields. Okay. Explicit forms we will discuss when we go to the waveguide problem or the resonator problem. Here we are giving an outline of the resonance phenomenon and how the loaded resonance, as we saw through our power conservation, is different from the source free resonance and why the source free resonance is important. Okay. So, using the source free resonance we can know the particular mode which is responsible for this resonance, and if we know the mode we can better design our probe or our exciting structure to better couple to that mode. In fact, it works a little bit reverse way, that the vendors give us a specification that I want my, let us say, my antenna to radiate in this way, which can be called a end fire direction. So, this is an end fire direction, or it is called a vertically polarized pattern, because the polarization is like this, it is vertical, or I want to radiate in this one, or which is called a broadside pattern. So, this kind of pattern is typically used in vehicular communication, a ship to ship communication or a vehicle to vehicle communication, when we want to communicate along this direction, along the horizon, and this kind of pattern is used for communicating with skybound targets, satellites, rockets, space vehicles, aircrafts. So, this kind of pattern is useful. So, the typically with the vendor will give you a specification that I want a end fire pattern or want a broadside pattern at a particular resonance. So, then you have to identify which kind of modes lead to this kind of pattern or this kind of pattern. Typically but not always, TE to R modes lead to broadside pattern and TM to R modes lead to end fire pattern. What I mean by TE to R is that if this is the radial direction, this mode means ER equal to 0. That means, the only relevant component for this mode for the TE to R is E theta, E phi, H r, H theta and H phi. Similarly, for this mode it is TM to R, transverse magnetic to R, that means its HR is 0, HR component, the radial component is 0. Therefore, its field components are ER, E theta, E phi, H theta, and H phi. So, typically Tm to R, typically but not always, typically Hm to R, Tm to R will give an end fire pattern and T to R will give broadside pattern, but there are T to R modes which give end fire pattern. So, be careful. So, typically the vendor will give you the specification, this is the pattern I want. So, you want to start from that mode, I want to excite this mode, then you want to design your feed, that where will you put, how will you put the feed, and find the resonant frequency from the characteristic equations which is obtained from here. So, the source free resonance is very meaningful, because it helps us to design the system, it helps us to give a physical insight to the system, whereas the loaded resonance enables me to find a match. The most important concept of the loaded resonance is getting a match, because the loaded resonance is intimately linked with the concept that I want to match my probe to the feed line here, or to match my DRA with the probe here. Okay. So, the concept of loaded resonance is deeply embedded to this match. So, we will continue, let us stop here, we will continue on the significance of the power conservation. Thanks.